Since we're addressing a global issue here of humans' impact on our planet, it's worth stepping back for a moment and taking a look at the large picture. The first remarkable thing to note, as the Harvard entomologist E.O. Wilson has pointed out, that the biomass of human beings is 100 times that of any large animal that has ever existed on Earth. You hear people say the world's population is 7 billion, but that was a while ago. The population today is 8 billion. It took 300,000 years for humans to go from the first pair to 1 billion in 1820. It took a mere 10 years to get from 7 billion to 8 billion. We are having planetary impact. More remarkable, though, is our energy use. Every creature, every living thing on this planet uses 1 times its metabolism rate. The metabolism rate of a human being is 100 watts. That is, the energy one needs to take in food and drink and air, amounts to 100 watts of energy. A cockroach, an elephant, and anything in between uses precisely 1 times its metabolic rate. Only humans master other forms of energy to make their life more comfortable. And in fact, in the United States, we use 10,200 watts of energy per person. That is, we use 100 times our metabolic rate to keep our temperature comfortable, to transport us around the planet, to manufacture the little widgets that we like. 100 times our metabolic rate. That means we have 100 times the impact on the planet. As Richard Alley of Penn State has pointed out, it's as though every one of us has 100 serfs taking care of every one of our needs. And 100 serfs produce a lot of waste. We've been producing a lot of waste, and we've been dumping it in the atmosphere in the form of carbon dioxide and other greenhouse gases. Indeed, worldwide, per capita energy use is about 2,575 watts. So even averaged over the Earth, it's 27 times the average metabolic rate of a human being. The total world power consumption today is 20 trillion watts. It's important to note, though, that that's a small number compared to the amount of solar energy hitting the Earth, as we'll see in a minute. Now, the problem of global warming and the impact that humans are having on it has been discussed more intensively over the last 5 years or so. And there's a clear mandate to reduce our dependence on fossil fuels. So one might ask how we're doing. I have here the total current US energy use by subject matter from 2016, the year after the Paris Accords, and in 2020, 5 years after the Paris Accords. You see, our fossil fuel use went from 79.9% of our energy use to 78%. Not exactly a dramatic decline over 4 years. Nuclear, biomass, and hydropower have remained roughly constant. In terms of hydro, we've dammed most of the rivers that we can dam to generate electricity. Wind, an ultimately renewable resource, went up by 50%, but that 50% was from 2.1% to 3.1%, still a trivial fraction of our total energy use. Solar energy doubled, but from 0.6% to 1.3%. This compares unfavorably with most of the developed world. Indeed, the leading country, Denmark, generates more than 50% of its energy from solar and wind already. Now, in thinking about how to move forward with this problem and wean ourselves from our fossil fuel dependence, it's important to recognize that we have an electric grid that needs to be fed all the time, not just when the sun is shining, not just when the wind is blowing. And so we calculate for each kind of energy generation facility what we call the load factor, which is the fraction of the maximum output that the plant can produce. So what fraction of the time is it producing at 100% capacity? The answer is, for solar energy, that number is 20 to 25%. Obviously, it produces none at nighttime, so there's half of it right there. And then on cloudy days, production rate is way down. Wind, depending on where you cite it, is somewhere between 35 and 40% of its maximum capacity because the wind isn't blowing all the time. Fossil fuel plants, oil, coal, and natural gas, typically operate at 55 to 65% of their maximum capacity. Nuclear power plants, on the other hand, operate at 95% of their maximum capacity. These are all numbers that need to be taken into consideration when designing the future of the next few decades and how we're going to go from a fossil fuel-dependent economy to one that depends on renewable resources.